Good morning, everyone. In this session, we are going to discuss about the Unit 1, Part 3, that is search algorithms. So, what are these search algorithms and what are these search strategies? Let us discuss in this session. And coming to the types of search algorithms, based on the search problems, we can classify the search algorithms into two, that is uninformed and informed search algorithms. And we can also say that this uninformed search as blind search and informed search, or also we can also call it as the heuristic search. And coming to uninformed or blind search, we have six algorithms, that is BFS. In this, the main two are BFS and DFS, and UCS, depth limited search, iterative deepening DFS, and bidirectional search. And coming to this informed search or heuristic search algorithms, we have only two algorithms mainly, that is best first search and the A star search. So before going to discuss about this informed or uninformed, let us first differentiate what is the different uninformed and informed. This uninformed search will search without any information. It is going to search for a solution, whereas informed search, it is going to search for a solution with the prior information. And there is no knowledge about the goal state in uninformed search. It is going to use some knowledge to find the steps to find the solution. It is time consuming. Why? Because as it has no knowledge, but coming to the informed search, it gives us the quick solution. And in terms of time and space, it requires more complexity and it requires less complexity. DFS and BFS are the best examples for this uninformed search. A star and best first search are the best examples for this informed search. So today in this session, let us discuss in depth about this uninformed search algorithm. Coming to this uninformed search algorithms, whoever it may be, either humans or AI, we need to think of all the possible ways to reach the goal state if there exists a goal state. That is from the initial state, all the consequences, etc. Similarly, even these AI systems also uses various search algorithms for a particular goal state. As the name itself indicates, uninformed search means machines blindly follow the algorithm regardless of whether right or wrong, efficient or inefficient. These algorithms are brute force operations. This is one important. That means they don't have any extra information about this search space, and the only information they have is how to traverse or visit the nodes in the tree. That's why these uninformed search algorithms are also called as the blind search algorithms. And they don't have any background information or how to approach goal or whatever it may be. But still, these are the basics of search algorithms. That's why these uninformed search algorithm plays an important role in AI. But before going into these search algorithms, let us see some terminologies which we will be using throughout this search strategies. That is a state. We know that it provides all the information about the environment, or also we can also say that it is the initial state, and there will be a goal state and path or step cost. That is the cost. What is the cost? These are integer. A cost may, in terms of integer, we are going to give. That is how to reach from one node to another node. What is the cost? And then space complexity and the time complexity. That is amount of space our memory and algorithm takes in terms of input, and the time complexity is the amount of time the algorithm takes in terms of input to the algorithm. And we are also going to use three terms, that is B, that is a branching factor, D, depth of the least cost solution, and M is the maximum depth state space. So these are all these things we are going to use when we find the time complexity or space complexity of a particular algorithm. The very first and foremost important algorithm is the depth first search algorithm. So it is a search algorithm where the search tree will be traversed from root node, and it will be traversing or searching for a key at the leaf of a particular branch. Here, if the key is not found, the searching retraces its steps back to the point where the other branch was left unexplored, and the same procedure is repeated for the other branch. So let us explain. This, with the help of a diagram, there is an image. You can look at this image. With this is the, let us say, this is the initial state and this is the goal state. How we are going to reach from initial to the goal state with the help of a depth first search algorithm. So here, the search starts from the root node A. So from here, the search starts. Why? Because this is the initial state or the start state, and then goes to the branch where the node B is present. Here we are going to follow the lexicographical order. That is alphabetical wise we are following. That's why from A, yes, definitely it will traverse to the root node B. Then it goes to node D because of DFS, and from D, see here, from A to B, and after B, we have two options. B can go to D and B can go to D. But as we are following the lexicographic order, from B, it is going to go to D. And from D, yes, definitely it will go to H. As after coming to H, there is no exploring of the nodes. What DFS follows is it is going to backtrack to D, then backtrack to B. Again, the right side it is going to explore. So now B from E goes to E, and from E there is a chance of exploring two nodes. After E, it explores I, then again we backtrack to E, then it explores the node J. In one depth means it will travel, goes into one depth. It is traveling in one depth and it has visited all the nodes. Now it will backtrack to the root node, that is it will reach to the node A. Now it will traverse into another depth of the tree, that is from A it goes to the C, and from C there is F and G, but as we are following the lexicographic order, after C it is going to explore F, and from F, as there is no other option, it will goes to the K. So if this is our goal node, there itself it is going to stop the process. Otherwise, if our goal node is G, then again it backtracks to F. From F, it is going to backtrack to C. Then it is going to visit the goal node G. In this way, the depth first search algorithm works. So here, the main important points regarding this depth first search algorithm is, first thing, the first point is it is uninformed search algorithm, and it is going to use the stack data structure, that is last in first out, and it is going to travel to deepest node, that is in one side it is going to travel into depth of a tree. It visit all the nodes, then it comes to the root node, and then only it is going to traverse into another depth of the node. So that's why we say that it is a travels to deepest node. And coming to the solution, whether it gives a complete solution or not, yes, it doesn't give the complete solution. We can say that it is a incomplete one. That is, it is non-optimal solution it is going to give. That is what the disadvantage with the depth first search. It gives optimal solution? No, it doesn't give. It is going to give us a non-optimal solution. Okay. So coming to the advantages of this DFS, it requires very little memory. Why? Because it requires to store a stack of the nodes from the root node to the current node, and it takes less time to reach the goal node compared to the other algorithm, the next coming algorithm, that is the BFS. But coming to this disadvantages, that there is a possibility that many states keep reoccurring and there is no guarantee of finding the solution. What I told you, that it is going to give us the non-optimal. And the other disadvantage is it goes deep down searching, and sometimes chances are there that it may go to the infinite loop. And coming to the conclusion, the very important point is it occupies a lot of memory space and time to execute when the solution is at the bottom or end of the tree. And this particular DFS is implemented using the LIFO stack data structure. Is it complete? No, it's not complete. And coming to the time complexity, it is order of B to the power D, not M actually. We can also say that M, but it is order of b to the power of d, where b is the branching factor. So what do you mean by this branching factor? So when we have a node of 2 children or 3 children, sometimes we may have 2, sometimes we may have a 3. So let us conclude that here the branching factor is 2, and depth, D indicates the depth of a tree. That is, let us say at the fourth level, and the depth is maybe after 2 levels you got a solution. Then we can say that 2 into 2 square, then we can say answer is 4. That is, after 4 searches, we have got the goal state. In this way, we are going to find out the time complexity and space complexity. That is order of b power d. Okay. And another way to find out this time complexity and space complexity is order of vertices plus edges. That is, v equal to number of vertices or nodes and v equal to number of edges. In this way also we can find out the time complexity and space complexity. We know that these are all vertices and we know that these are all edges. So in these two ways we can find out the time complexity and the space complexity of this depth first search. So in the next session, I'm going to discuss about the breadth first search. Thank you.